Alright, well you can see what problem we're working on here. I wrote out the answers. I thought I'd write them out at a time, talk about them a little bit. Okay, so what does R squared mean? R squared is really low. Only 1.3% of the variation in swim time in minutes across Lake Ontario is accounted for by variation in the year the swim was made. Or in other words, only 1.3% of the variation is accounted for by the LSQR model based on change in year. Are the swimmers getting faster or slower? Well, the coefficient of year, which is in this little table here, so year is 5.14, that is the slope. That's B sub 1. B sub 0 is negative 8950. That's probably a really huge negative number because probably they used years, the actual years, in creating the model. That's my guess, anyway. Now, before I forget, I want to say something about this model here, this residual model. Notice that it's residuals versus predicted. Now, every time that we've analyzed residuals versus the x values. So the residuals would be in there for the y values, and then we would use the x values to explain them or whatever, and then we'd hope for a random association of the residuals versus x values. Now this graph has residuals versus predicted, and the predicted values are the y-hats. So how do you get the y-hats? Well, there's a very straightforward way to do it, and I explain how to do that in problem 31. And I would really like you to study problem 31, so at some point, maybe you can do it now, stop this recording, look at 31, so that you know how to make a residuals versus predicted, or sometimes they're called fitted values. Fitted is another word. So fitted, the following words are equivalent. Y-hats, fitted, predicted. These are all the same. They all mean the same thing. Okay? And like I said in the video for problem 31, I show you how to produce a residual scatter plot that is residuals versus the fitted values, or the predicted, or the y-hats. Now, anyway, the coefficient of year is positive 5.14, so the time required to swim the lake is increasing. However, R squared is so low that we put very little faith in this model. So only 1.3% of the variation, that means 98.7% of the variation in swim time is not accounted for, is reflected in the residuals, and is accounted for by other variables other than change in year. Moreover, there is a huge residual, namely this residual right here, okay, and that we're going to talk about that in a minute. So that casts further doubts on the validity and the usefulness of this model. Finally, the outlier seen in the residuals plot is a crossing by Vicky Keith in 1987, in which he swam a round trip. Now, all the other measurements are one way. So this is this is an association for which the population is the time it takes to swim across the lake one way. And yet somebody had the bright idea of including the time it took somebody to swim round trip. So that residual does not belong, and makes the model less reliable. So, should it be removed? the outlier should be removed since the swim time is for round trip, and all the other times the round trip doesn't belong. But let's see, I gotta wipe this out. But removing it will not affect the model. Okay, and why? Because the x-coordinate of the outlier is close to the mean of the x-coordinates, so it has no leverage. It has no leverage, so it will not change. It's not going to change the slope of the LSQR. It may change the y-intercept a little bit, but we really don't care about that. Changing the model, that is having influence, means essentially changing the slope. So removing that point would not significantly change the slope of the line, B sub 1, which is 5.14171. Removing the point would strengthen R, and it would make R squared bigger. But it would not change the model a lot.